Episode 12. Title of the course is Advanced Material Science, Unit 3. In this episode 12, we will discuss about spontaneous polarization and domains in BaTiO3 and also discuss piezoelectricity. Spontaneous polarization and domains in BaTiO3. The structural change in BaTiO3 crystal due to lattice variation gives rise to ferroelectricity. Above 120 degrees Celsius, BaTiO3 has a cubic crystal structure with the titanium ions exactly at the body center. Barium ions are at the body corners and oxygen ions are at the face center. At those temperatures, there is no spontaneous dipole moment. If the crystal is cooled below 120 degrees Celsius, the titanium ions shift to one side of the body center. This displaces the neighboring ion along one of the crystal direction, which becomes elongated. This direction is the C direction of the tetragonal structure obtained due to the shifting of the titanium ion. The displacement of the titanium ion creates electric dipoles, and all the dipoles of the adjacent unit cell gets aligned in the same C direction. Similarly, at 5 degrees Celsius, spontaneous polarization direction corresponds to the phase diagonal direction, and at minus 80 degrees Celsius, the direction corresponds to the body diagonal. At those temperatures, there is an enormous value of dielectric constant. In fact, BaTiO3 has more transition temperatures. Since ferroelectric material are similar to ferromagnetic material, they exhibit domain structure just above the Curie temperature, that means 120 degrees Celsius. The barium titanate has the cubic structure, but as the temperature falls, it becomes slightly tetragonal. The polar direction in the crystal is the C axis of the tetragonal cell, which coincides with one of the former cubic axes. In a specimen crystal, the tetragonal axes of different regions have different direction of spontaneous polarization. These different regions are called domains. The index of refraction of BaTiO3 parallel to the tetragonal C axis differs from the refractive index at the angles to the C axis. Since it is transparent material, it is possible to send polarized light through a specimen plate of BaTiO3 and view the emergent light with an analyzer. The domains then show up as dark and bright bands. Thus, we can see shaped laminar domain in barium titanate. It is found that the domain wall, unlike the magnetic domain wall, is only a few atomic spacing thick. Then we will discuss about applications of ferroelectric materials. Ferroelectric energy converter. Ferroelectric crystal exhibit the pyroelectric effect. That means a change in the temperature of the crystal produces a change in its polarization. Using this effect, one can convert heat energy into useful electrical energy. The efficiency of the conversion is about 5.6, that means theoretical value. First, the capacitor with BaTiO3 is charged to a voltage of V1 at the temperature T1 just below the Curie temperature theta. Now, capital Q equal to C1 V1, where C1 is the capacitance of the capacitor. Initial energy is equal to half Q V1. that is also equal to area of the triangle ABC. Now the capacitor is isolated from the battery and it is heated up to T2. Therefore, the dielectric constant epsilon R decreases. For BaTiO3, when we increase the temperature from 15 degrees Celsius to 30 degrees Celsius, value of dielectric constant at 15 degrees Celsius divided by value of the electric constant at 30 degrees Celsius, that is equal to epsilon R1 divided by epsilon R2. The value is 5. Since the dielectric constant value decreases, the capacitance value also decreases, and at temperature T2 the capacitance of the capacitor is equal to C2. That means C2 less than C1. Since the charge Q in the capacitor is constant and C2 less than C1, then capital Q is equal to C1 V1, that is also equal to C2 V2. V2 is greater than V1, then V2 is equal to V1 C1 divided by C2, that is also equal to V1 epsilon base R1 divided by epsilon base R2. Increase in energy del W is equal to half Q into V2 minus V1. The capacitor is now discharged through the load resistor capital R and a rechargeable battery of voltage capital V to get electric power. The capacitor should be cooled to T1 to complete the cycle. The high dielectric constant of ferroelectric crystal is also useful for storing energy in small size capacitors in electrical circuit. In optical communication, the ferroelectric crystals are used for optical modulation. These are used in electroacoustic transducers such as microphone. Ferroelectric crystal exhibit the piezoelectric property. Using this, we can find enormous application of ferroelectric material. Then the next topic, piezoelectricity. When certain crystals subjected to compression or tension exhibit opposite kind of charge at the opposite face of the crystal, the charges produced on each face are always equal in magnitude and are proportional to the total force applied. Materials which are polarized when subjected to mechanical deformation are called piezoelectric material. Ferroelectric crystal always exhibit the piezoelectric property. Piezoelectric materials are very important since they permit the conversion of the mechanical energy into electrical energy and vice versa. The quartz crystal is very good example for this piezoelectricity. Natural quartz crystal has the shape of hexagonal prism with the pyramid attached to each end. The line joining the end points of this pyramid is called the optic axis or z-axis. The quartz crystal is cut into hexagonal plate by cutting perpendicular to the optic axis. A line joining the opposite corner of the hexagon form the electrical axis or x-axis, while those joining the midpoint of the opposite sides forms the mechanical axis or y-axis. There are opposite charge along the electrical axis when a stress or tension is applied along the mechanical axis. Thin plates of the quartz crystal cut perpendicular to x-axis are known as x-cut plate, whereas those cut perpendicular to y-axis are known as y-cut plate. At AT, cut crystal is cut from a plane rotated about x-axis and a line is in the y-z axis, making an angle 35.5 degree with z-axis. The important thing is electrical equivalent of the quartz crystal and its electrodes. Then quartz crystal with x and y axis. A two-dimensional structure with piezoelectric property. The dashed triangle lacks a center of symmetry. The mechanical system of quartz crystal may be represented by the equivalent electrical circuit. The mechanical resonance is equivalent to a series tuned circuit, and this is by capacitance C1 of the electrode. Typical values are given below. X cut quartz, that means length by vibration. Dimension is to rectangular ball. Small x equal to 1.4 mm, y equal to 30.7 mm, z equal to 4.1 mm, capital R equal to 15000 ohm. C1 3.54 picofarad, capital L equal to 137 Henry, capital C equal to 0.0228 picofarad, F not equal to 89.87 kilohertz. AT cut quartz, dimension is to disc, 25 mm diameter, thickness 1.10 mm, capital R equal to 24.2 ohm, C1 equal to 17.9 picofarad, capital L equal to 0.119 Henry, C equal to 0.0945 picofarad, F naught equal to 1500 kilohertz. Thus, one can produce acoustical vibration from 25 kilohertz to 50 kilohertz using this crystal. Particularly at AT cut crystal is suitable to produce high frequency. Only non-centrosymmetric crystal exhibits the phenomenon of piezoelectricity. A hypothetical two-dimensional model of a crystal lacking in the center of symmetry is one of the important things. The two-dimensional lattice is hexagonal and has a point group symmetry 3m. Before the application of tension, the resultant dipole moment at each lattice point is 0. Suppose a tension is applied along the direction x direction, the angle theta increases, giving rise to a polarization in the positive y direction. But if the unit is compressed along the x direction, theta decreases and polarization is along the negative y direction. From the above, we know that piezoelectricity is related to symmetry of crystal, and it is excluded from all structures having a center of symmetry, because in the centrosymmetric system the opposites ends in every direction and identical, and hence the application of tension or compression produces no polarization all. Next, we will discuss about applications of piezoelectric material. In the construction of crystal microphones, phonograph, reproducers and sound pickups, the piezoelectric materials are widely used. A salt crystal, when mechanically articulate with properly mounted phonograph needle, will be subjected to a variable pressure as the needle follows the groove in the record. This will in turn produce a variable EMF, and hence the mechanical or sound vibration can be transformed in electrical oscillations. Similarly, when the sound waves fall on a disc which is fixed on the crystal, the latter is subjected to variable pressure, and this will in turn produce variable current. We can produce high frequency oscillation in quartz or barium titanate. An alternating PD of 50,000 volt at frequency of 3 MHz is imposed between the foil at the two ends of the quartz crystal, which begins to vibrate rapidly. If the natural frequency of the mechanical vibration of the quartz crystal coincided with that of applied EMF, then on account of resonance, the vibrations are well maintained. Such an Arrangement is used for stabilizing frequency in transmitting radio station, and also as standard of frequency it is used to produce ultrasonic waves which are used in non-destructive testing of material and a diagnostic aid in medicine. Piezoelectric material are further discussed under acoustic material under their application. Dear student, now we are in the end of unit 3. Next we will solve some important problems and discuss some important questions. First, problem solving. Find the value of insulation resistance of a dielectric whose volume resistivity is 5 into 10 to the power 16 ohm meter and surface resistivity of 10 to the power 18 ohm. The dimension of dielectric are follows. The thickness through which current flow is 5 cm. The length of the dielectric is 8 cm. The width of the dielectric is 3 cm. Capital R equal to rho small l divided by capital A. Then we know R equal to 5 into 10 to the power 16 into 5 into 10 to the power minus 2 divided by 8 into 3 into 10 to the power minus 4. Now we can solve. The answer is 10 to the power 18 ohm. Now we should calculate R base S. The formula for R base S is rho base S x by y. The value of x is equal to 4 plus 5 plus 4, that means 13 centimeter. Length of the surface current path. Y is 3 centimeter. The perpendicular length width of the surface current path. Now we can substitute this x, y, rho values on RS equation. Then RS equal to 10 to the power 18 into 13 divided by 3. The answer is 4.33 into 10 to the power 18 ohm. Now we can calculate insulation resistance capital R base I. The formula for capital R base I is capital R base S into capital R base V divided by capital R base S plus capital R base V. Now we can substitute these values to this equation. 10 to the power 36 into 4.33 into 1 divided by 10 to the power 18 into 4.33 plus 1. The answer is 0.81 into 10 to the power 18 ohm. This is the final answer for insulation resistance. Dear student, then we will move on to another problem. An insulating material is kept inside the parallel plate capacitor. The distance between the plates is 1 millimeter and the area of each plate is 10 to the power 4 millimeter cube. The resistivity, relative permittivity and power factor tan D are 10 to the power 10 ohm meter, 8 and 0.1 respectively. Calculate the dielectric loss for DC and AC voltage of magnitude 1 kV. The power frequency is 50 Hz. This is the problem. Now we can solve this problem by using the formula capital R equal to rho L divided by capital A. Just we can find capital R base V equal to 10 to the power 10 into 10 to the power minus 3 divided by 10 to the power 4 into 10 to the power minus 6. Now we can get the R base V. Answer is 10 to the power 9 ohm. Then we will calculate DC dielectric loss. The formula for DC dielectric loss is capital V square divided by capital R. Now we know V and R value, then we can substitute in this equation. It gives 10 to the power 6 divided by 10 to the power 9. The answer is 10 to the power minus 3 watt. That is DC dielectric loss. For a parallel plate capacitor, capital C, the formula is capital A epsilon naught epsilon R divided by small d. Then we know about AC dielectric loss. The formula for AC dielectric loss is capital V square 2 pi f c tan sigma. Now we know the all values, then we can substitute these values, we can get the answer. 10 to the power 6 into 2 pi into 50 into 10 to the power 4 into 10 to the power minus 6 into 8 into 8.84 into 10 to the power minus 12 into 0.1 whole divided by 1 into 10 to the power minus 3. The final answer is 22.22 into 10 to the power minus 3 watt. This is the final result. The next problem. The radius of the helium atom is about 0.55 Armstrong unit. Calculate the polarizability of helium and its relative permittivity. The number of helium atom in a volume of 1 meter cube is 2.7 into 10 to the power 25 atoms. Now we know the formula for alpha base E is 4 pi epsilon naught r cube. We know the epsilon naught value and r cube value, then we can substitute in this equation. 4 pi into 8.84 into 10 to the power minus 12 into 0.55 whole cube into 10 to the power minus 30. The alpha E final value is 0.185 into 10 to the power minus 40 Faraday meter square. Now we can calculate epsilon r. We know that capital N alpha E equal to epsilon naught into epsilon r minus 1. From this equation we can find epsilon r. Epsilon r equal to capital N alpha base E divided by epsilon naught whole plus 1. We know the value of capital N, alpha E, epsilon naught, all values. Now we can calculate epsilon r. 1 plus 2.7 into 10 to the power minus 25, 0.185 into 10 to the power minus 40 divided by 8.84 into 10 to the power minus 12. The final answer is 1.000057. This is the final answer. The next problem is a capacitor uses aluminum oxide as the dielectric with relative permittivity is equal to 8 and effective surface area of 360 centimeter square gives a capacitance of 6 microfarad. Calculate the field strength and the total dipole moment induced in the oxide layer if a potential difference of 1.5 volt exists across the capacitor. Now we know the formula capital E equal to V divided by small d. We know also small d expression. Small d is equal to epsilon naught epsilon r capital A divided by C. In this equation we can find capital E. Now capital E becomes VC divided by epsilon naught epsilon r into capital A. Now we can substitute V, C, epsilon naught, epsilon r and capital A values in this equation, we can get the capital E value is 3.535 into 10 to the power 7 V by M. Total dipole moment is equal to epsilon naught into epsilon r minus 1 into E into volume of the dielectric. Then the equation becomes epsilon naught into epsilon r minus 1 into V into area of the dielectric. Now we can substitute all the values. Total dipole moment is calculated. The calculated value is 33.4 into 10 to the power minus 1 to centimeter. The next problem is a parallel plate capacitor has an area of 8 cm square with a separation of 0.08 mm. The space is filled with polystyrene. The real part of the relative dielectric constant is 2.56 and the loss tangent is 0.7 into 10 to the power minus 14 at a frequency of 1 MHz. Calculate the capacitance and the equivalent parallel loss resistance. We know that capacitor with lossy dielectric is equal to ideal capacitor with a parallel resistor indicating dielectric loss. We know the formula for capital C is capital A epsilon naught epsilon r divided by small d. We know the values of capital A epsilon naught epsilon r and d value. We can substitute these values in this equation. We can get the capacitor lossy dielectric value capital C is 226.3 into 10 to the power minus 12 Faraday. The loss resistance is given by capital R is equal to V divided by I, that is also equal to capital E naught small d divided by capital J double dash capital A. In phase component of current density, capital J double dash is equal to epsilon naught epsilon r single dash omega capital E naught, where epsilon r double dash is the imaginary component of relative permittivity. Out of the phase component of current density is equal to epsilon naught epsilon r single dash omega capital E naught. Tan sigma is equal to epsilon r double dash divided by epsilon r single dash. The value is 0.7 into 10 to the power minus 4. Now we know all the values, then we can calculate capital R value. Now the capital R is become small d divided by epsilon naught epsilon r double dash omega capital A. Now we can calculate it. Capital R is 10 mega ohms. Summary of the unit 3. Dielectrics are non-metallic materials having high resistance and negative temperature coefficient of resistance. Inducement of electric dipoles in a dielectric material in the presence of electric field is called polarization. Dielectric constant measures the amount of abstraction offered by the material for the passage of electric current. Dielectric strength is the minimum voltage required per unit thickness of the material to produce dielectric breakdown or dielectric failure. When a dielectric loses its insulation resistance and permits large current to pass through it, it is said to a breakdown. Local field is the space and time average of the electric field acting on a particular molecule. Materials which exhibit electric polarization even in the absence of applied electric field is known as ferroelectric material. Piezoelectric effect refers to the creation of voltage by means of compression or tension acting on certain type of crystals like quartz. Dear students, thank you. We will start the unit 4 on next episode.